Hi everybody. Today I'm going to talk to you guys about collisions, and this is our first sort of introduction to the topic here. And we're going to put aside the idea that there are different types of collisions, and then of course explosions, which are interesting with related to collisions as well. But we're going to put that aside until the next video, 43. For this one, we're just going to introduce the main topic, and the main topic is what is a collision, and then how can we analyze it mathematically. And so it has to do with this thing called the law of conservation of momentum, which I've written down here. You may not understand what these symbols mean, so we're going to go ahead and talk it through here with an example. So hopefully this makes sense. Okay, so we have this situation where we have a mass 1, which is 1 kilogram, which happens to be moving to the right at 4 meters per second. And I've indicated that it's moving to the right by a positive right there. I've decided that right is positive, as most people do. And in the picture here, it's shown as a vector. Okay, so if I wanted to, I could say that it has this initial momentum for this shape 1, and I'm going to put an I here so that we know it's initial, is equal to 1 kilogram times 4 meters per second, which gives us 4 kilogram meters per second. And hopefully nobody's lost by that point right there. That's just a review from the last couple of videos there. So if I wanted to, I could also draw a momentum vector. That would also be 4 kilogram meters per second long in the rightward direction. So it has this vector sum right there, or the vector product right there. Okay, so it's moving that way. It happens to be on a collision course with mass 2. And mass 2 is a little bit bigger, right? So it's 2 kilograms. And it happens to be moving to the left at an initial speed of 1.0 meters per second. And so it's indicated here that it's moving to the left by this vector, right? And I've indicated here that it's moving to the left by the negative sign. Because I decided that right is positive, I must have decided also that left is negative. And so if I go ahead and do this here, I end up with a momentum, that's a vector, right, for object 2 in the initial state that's equal to its mass, 2.0, times its its velocity, which is negative 1.0. And so as a result, I end up with a momentum that is negative 2.0 kilogram meters per second. So if I wanted to, I could draw it out like so. Like that. That would be the momentum vector. Okay. So when they collide, these two objects happen to be really, really sticky. So when they collide, they stick together and then move off together based on the rules that govern collisions. And so what are the rules that govern collisions? Well, the first one is this law of conservation of momentum right here. And that says that if you add up all of the vectors at the beginning for momentum, the sum of those vectors must be equal to the sum of all the vectors for momentum at the end. And so as a result, we can take a look at these momentum vectors that I've drawn up here. First off, you can just see, just from a gut instinct, you can see that this momentum vector is much longer to the right than this momentum vector is to the left. And so if I were going to add those two together, I would end up with some momentum still to the right, because this would only cancel out a small amount of that. And so if I go back up here to the actual numbers, I've got a positive 4.0 kilogram meters per second plus a negative 2.0 kilogram meters per second. So what's positive 4.0 kilogram meters per second plus negative 2.0 kilogram meters per second? The sum, so I'm going to write that as a sigma here, the sum of all the initial momenta must be positive 2 kilogram meters per second. The positive, I just keep forgetting to do that. The positive indicates that it's still to the right, and the 2 gives us some numerical value for it. Okay, so that initial sum of all the momenta must be equal to the final sum of all the momenta. Now, look what happens. When they collide, they hit, something happens where they stick together. And so instead of two different objects, now I have one object that has the combined masses of both. And so this new object, I'm going to use a capital M just so you can see that it's a new object, has the mass of 1 plus the mass of 2. So what is that mass? 1 kilogram plus 2 kilograms gives me a total mass of 3 kilograms for the new object. Okay. Now, I know that the momentum for the whole thing must be in this direction, and it must be final momentum, the same thing as the initial. But there's only one object, so this one object has all of the momentum right now. So I know that that total momentum must be positive 2.0 kilogram meters per second. Now I know it has a mass of 3 kilograms, so I can relate this back to the momentum formula, which we learned a couple videos ago, which says the momentum is equal to the mass times the velocity. Okay, so here's what the momentum must be. So we can put that in right there. And here's what the mass must be of the new single object that's made up of the two together. So can we solve that for V? Of course we can, right? And so I bring the mass to the other side, and I end up with V, in this case, equals the momentum divided by the mass, which we know, I should say this is the final velocity here, which we know is 2 kilogram meters per second divided by 3 kilograms. So you can see the units must cancel out, so therefore we get 2/3 meters per second. Now, you might remember that I don't like fractions because fractions imply infinite significant figures. And so as a result, we have to kind of go back to how many sig figs we have here. So that's 2. So I'm going to go ahead and use 0.67 meters per second as my final answer. So what did we do? We took two objects that were going to collide and used this idea of the law of conservation of momentum, knowing that the total momenta for the system at the beginning must be equal to the total momenta for the system at the end. And so I added these vectors, momentum vectors, together, and it must be equal to all of the object's momentum vectors here, but we only have one object at the end. There are many instances where we'll have more than one object, and so then you'll have to add up all those vectors to try to figure out what the total momentum is. But now you've got the basic idea. What happens, the reason why this happens is because when they collide, I want you to think about it this way. Let's imagine we're only looking at M1 for a second here. M1. So the moment it collides with M2, M1 applies a force this way, and we'll call that the action force. So you can already see where I'm headed with this. If you remember action and reaction forces, you already know where I'm going. So M1 applies a force to M2 to cause it to change its motion when they collide. Because of Newton's third law of motion, we know that M2 must apply a reaction force that is equal to, but opposite direction of, the same action force. And so we have this reaction force that's applied over here. As a result, we could go ahead and use Newton's second law of motion, which you may remember is F equals ma. Get rid of that. There we go. So we could use F equals ma to be able to do the same solution, to get the same solution that we got up here, but for each object. But this seems like a much shorter cut. So we're actually using momentum as a shortcut to try to get to the answer. And it's because of this Newton's third law and Newton's second law combination. But really the reason why both objects change their momentum is because of Newton's third law. Because in every force, there's also a reaction force. In every interaction, there's always a pair of forces that act on different objects. And so that's why both objects are going to change their motion, and therefore their momentum. We could call those forces, because they're applied over a certain period of time, an impulse if you wanted to. So we've got an impulse here, and we've got an impulse here. And boy, this pen really doesn't like M's for some reason. And we know that an impulse must equal, because of the impulse momentum theorem, a change in momentum. And so if we have an impulse for this object, it's changing its momentum. And we have an impulse for this object, it's changing its momentum also. And so we're kind of wrapping up a lot of the ideas, or putting them together in such a way so that we can see how this works. So we've got impulses, all the momenta is conserved, and it's because of Newton's third law. Perfect, we got through it all. Excellent. If you have any questions, please let me know. Thanks for watching.